that's the plan. And I think, yes, so we have, yes, the number of attendees are still growing, but I think it's a good idea to start just to keep ourselves according to the schedule. So without further ado, John, you can put up your slides. Yes, and it's my great pleasure to introduce John Colliger, who will give a talk about separations and equivalence between ternstile streaming and linear sketching. It's a joint work with Eric Price. Okay, go ahead.
Thank you. Yes, so I'm just going to give you a quick 5-minute overview of our work on separations and equivalences between ternstile streaming and linear sketching. So this is joint work with Eric Price. So streaming algorithms are a class of algorithms for very large data sets that arrive one piece at a time. So imagine receiving the friendship graph of some large social network, one friendship at a time. And what we're going to be concerned about here is how different models of streaming computation relate to one another. So in particular, we're going to be concerned about 3 models. Firstly, the insertion-only model, where an algorithm only has to handle additions to a data set. Secondly, the turnstile model, where an algorithm has to handle both additions and removals from a data set. And thirdly, the linear sketching model, where an algorithm is only allowed to keep state linear in the input it's seen so far. And so what we want to know is, how do these models relate to one another? Well, it turns out that in one direction, this is pretty easy to establish. So firstly, any turnstile algorithm is trivially also a valid insertion-only algorithm, since as it can handle insertions and deletions, it can also handle insertions. And linear sketches turn out to also be turnstile algorithms, because as the state a linear sketch keeps is linear in the input it's seen so far, the output of the sketch will only depend on the final value of the data set, regardless of whether it was received as a series of insertions or a mixture of insertions and deletions. But that means what we want to know is, are these containments strict? So for the first of these, this turns out to also be quite easy to establish. By considering the minimum finding problem, there is an exponential separation between insertion-only algorithms and turnstile algorithms. But a surprising series of work, starting with Ganguly for deterministic algorithms and extended by Leeuwen and Woodruff to randomized algorithms, then further extended by Hooley and Woodruff, says that turnstile algorithms and linear sketches are actually equivalent. So if a turnstile algorithm exists for a problem, a linear sketch with only slightly more space also exists for that problem. And this is a very significant result, because what it tells you is that you can use techniques that give lower bounds, that use properties of linear sketches, and use them to get lower bounds for arbitrary turnstile algorithms. However, there's 2 significant caveats to this equivalence. So the first of these is that for a linear sketch to exist for a problem, the turnstile algorithm in question has to be able to handle some very extreme streams, streams that are doubly exponentially long in length and which take exponentially large intermediate values. And the second is this reduction is non-constructive. Given a turnstile algorithm, it allows you to prove that a linear sketch exists, but it doesn't tell you how to find that linear sketch. And in fact, it doesn't even guarantee that it's possible to calculate this linear sketch in small space, just that the sketch itself can be stored in small space. And so our results in this work address both of these questions. So firstly, we show that we show that these restrictions these restrictions on when an equivalence exists are actually necessary, that there are problems for which a turnstile streaming algorithm exists that works and uses a logarithmic space when the stream is guaranteed to be suitably bounded in length or have bounded intermediate states. But for which any linear sketch requires at least polynomial space to work. And secondly, on the other hand, for at least for deterministic turnstile algorithms, we show how to make this equivalence constructive. So if you have we give an algorithm that can take a turnstile streaming algorithm and find and evaluate a linear sketch which only uses slightly more space. And I won't have any time to go into detail about either of these results, but just a quick word on how we prove these. So for separations, what we do is we take the problem of bounded degree triangle counting, which is known to require only logarithmic space in the insertion only model. And we extend this algorithm of Johari and Godsey to turnstile streams, which either satisfy a length bounding condition or a restricted intermediate state condition. And this gives this exponential separation because this problem is already known to require polynomial space in linear sketching. And then for the second, we show that if you have a deterministic turnstile algorithm, you can try feeding it different streams and find collisions in the state space of this algorithm and use these to find vectors that you can quotient out. And therefore construct a linear sketch for the problem. And that's all I have to talk about here. So I'm happy to take any questions.
Right, cool. Thank you. Any questions? So I have a question from my end. So what would you say are the most immediate open problems?
Okay, so this I guess will be an answer to your question, also to Sahel's question, which is just posted in the chat, which is it's the same. Yeah. So so there's several things. So one is this like bounded length under which this works. To get the separation, we require that the length be at most something like n to the 7/6, whereas the equivalence is known when the stream length is doubly exponential in length. So obviously that's a very big gap, and it'll be very interesting to know where kind of where that separation starts to exist, and I guess the other biggest one in my mind is whether this equivalence can be extended to randomized algorithms. So we have this constructive equivalence for deterministic algorithms, and the Lewin and Woodruff reduction gives a non-constructive equivalence for randomized algorithms, and so we know how to make this equivalence constructive under like very limited circumstances. Like you have to assume that the randomized algorithm stores all of its randomness, but nonetheless your constructive one then needs a random oracle. So it'd be interesting to know if that could be generalized. Cool.
So there are two more questions. I think we have time to answer the first one. So the second question, I guess you see it, right? Was the initial equivalence between turnstile and linear sketch shown using probabilistic method? And that's a question asked by Sayantan.
I'm not sure I entirely understand what your oh, I see. Not very close. So the original, as in, if you mean the original equivalence between deterministic turnstile and deterministic algorithms from this Ganguly 2008 paper, it's been a while since I read it, but my recollection is no.
I have no idea. So cool. Okay, so. Okay, maybe let's take the quick answer. Okay, so Ami Chakrabarti provided the answer to this question. I think no, not probabilistic method. I'm just a messenger. Mm-hmm. Okay, so maybe let's quickly answer also a question by Adam, and but very quickly. And so Adam asked, can you say a bit how your new turnstile algorithm exploits nonlinearity? The new example is very intuitive, but as you say, that's insertion only.
So, okay. So just since I guess some people probably don't know it. So the way that the original insertion only algorithm for the problem works essentially is that you try and like sample some constant number of this. So this is the problem of differentiating between a graph with like 0 triangles and theta n triangles in a bounded degree graph. So what you do in this algorithm is you try and sample like a constant number of seed edges and then just keep all of their neighbors. And so this works in like a constant degree graph with theta n triangles because there'll be like theta n distinct first edges of triangles that appear in the graph. And then if you sample that and you keep all of its neighbors, you'll get, you'll with good probability get at least one of the triangles and be able to tell which case you're in. So this algorithm kind of breaks down in the fully general turnstile setting because basically an adversary can use insertions and deletions to make intermediate stages of your graph not look anything like a bounded degree graph, as long as they then delete off all of the like invalid edges at the end. And so kind of what we're using is the fact that in either a bounded length stream, you can say that the graph will look like a bounded degree graph almost everywhere.
Yeah, so sorry, I'll have to stop you right now because we are, thanks again for very nice talk and for questions.
Thank you.
And the next speaker, oh, I think that you need to stop sharing your screen. Perfect, thank you. Chen, can you?
Share my screen?
Yes.
Okay. Okay, can you see my screen?
Yes, yes, it's perfect.
Okay, perfect. Okay.
So without further ado, Chen will give a talk about exploration. Well, all of you guys can see the title, and this is joint work with Sepper. Go ahead.
Okay, thanks everyone. Again, my name is Chen, and I'll be talking about our results on how to find the most biased column in a stream with limited memory. So this is the joint work with my advisor, Sepper Asadi at Rutgers University. So the problem we are considering is we are given n columns with unknown biases, and we want to find the most biased column. We name it column star. So also we are given a gap parameter delta, which is the gap between the most biased and the second most biased columns. So the problem actually has a trivial solution. We can simply toss each column O log n over that square times and pick the column with the highest empirical bias. So by a simple turn of the union bound argument, we can see that the column we pick with high probability will be the most biased column. So there's also a algorithm called median elimination proved by Evan et al., which reduced the sample complexity from O log n over that square to constant for each column, and find the most biased column with a high constant probability. So the idea is to use multiple rounds, and at each round, we remove a fraction of the columns and increase the number of column tosses for the rest by a multiplicative factor. So by carefully choosing parameters, we can show that both the probability for losing column star and the overall number of column tosses decreases exponentially as the round goes up. So the algorithm is efficient and correct. There's also a matching lower bound for median elimination in terms of sample complexity, which showed that any algorithm to find the most biased column with high constant probability has to have this number of column tosses. So median elimination basically solves the sample complexity problem. However, drawback is that it has to store all the columns, and in modern day large scale application, storage is more or less expensive. So we studied the space of the column tossing problem in our paper. So we studied the problem under the streaming column tossing model. So in the model, we are giving a stream of columns on the fly arriving, we read it to the memory. And for each arriving column, we can choose to toss it, we can choose to store it, and we can store we can toss the stored column to compare with it. But remember that if we do not store a column, we will lose it forever. So we define the memory complexity as the number of columns we ever stored in this process. So if we look into the algorithms we already talked, so for the naive algorithm, well, we toss the number of contours is not optimal, but we can simply fit it into a streaming model with only store one coin by on the fly replace the coin with the highest empirical bias. On the other hand, a median elimination algorithm has the optimal sample complexity, but it has to store all the coins. So it leads to our motivation. What is the trade-off between the sample and space complexity in this problem? So where our result is kind of surprising, we managed to show to find an algorithm that finds the most biased coin with high constant probability, optimal, asymptotically optimal number of coin tosses, and only store one coin. So that means there's actually no sample speed trade-off in this problem. So our algorithm is named game of coins, and the idea goes as follows. So for each coin we stored, we give it the budget and we name it the king. So that's why we have this quite cool name, game of coins. And for each arriving coin, we will increase the budget of the current king, and we will challenge the king with the arriving coin. So the challenge rules goes at multi-levels, and at each level, we increase the number of coin tossing with a multiplicative factor, same as median elimination. And the king is declared defeated only if it exhausts all its budgets. So I'm going to briefly talk about the analysis. So the number of coin tosses can be bounded because the number of possible budget we can collect is small. And also, when coin star arrives at the stream, it's guaranteed with constant high probability to be the king because it can decrease, it can defeat any other coin with high constant probability. And also, after coin star becomes the king, you have to make sure its budget never goes to zero. So this is actually the main argument in our one coin algorithm. We managed to show that this the budget of the coin star will behave like a random walk with unbounded step length. So although the number of step length is unbounded, we managed to show that with a high constant probability over the theta stream, the budget never goes to zero. So we also extend our results to top K coin with asymptotically tight result on sample and space complexity, and streaming top K the comparison, and multi-M bandits. So bear in mind that the multi-M bandit is a little bit harder, so we do not have that gap guarantee. So our memory is a little bit, so we currently only have the O-log star in memory. So we have some open problems. So the first one is for the multi-arm bandit. We do not have the gap guarantee. So can we get a single arm algorithm for this? And also we are interested in extended result to instant optimal bounds. So that's it. Thanks.
All right, cool. Thank you. Thanks for a very nice talk. We have time for a few questions. So the first question is by Sandeep Silval. What happens if the parameter delta is not known for the coins?
Yeah, good. That's actually the that's actually what I said about the multi-arm bandits, right? So the multi-arm bandit setup is that you do not know the gap parameter, but you are permitted to find the epsilon best arm, which means the empirical bias can be epsilon far from the optimal. So yeah, so that's the kind of question we are interested in as an immediate continuation of this project. And so currently we have the O-log starring algorithm, and we believe we can also work towards a one arm algorithm. Yeah.
Cool, thank you. And the second question is by Alexander Nikolov, and he asked, what does instance optimal mean here? Is the instance multi-set of coin biases? Is the ordering of the stream still worst case?
Good. So if you, if we actually, sorry, yeah. So you can say a ON over dot square sample complexity here. So this delta is the gap between the most biased and the second most biased coins, right? And so in the instant optimal bound, we are interested in not n over delta square, but the summation of 1 over delta I square, and where delta I is the gap between the most biased and the ith most bias code. You know, we are trying to get the instance of each, the gap of each instance. So it's named instant optimal bound. So I have to remark that we cannot get ON, the summation of 1 over delta I squared, because the lower bound should be should have a double log factor, which was proved by, I think, I forgot the author's name, sorry, but it's approved by law of iterations. And so, yeah, that's about instant optimal bound.
Okay, perfect. So thank you again for a very nice talk and for the question. And I think Sepide is next, right? Yeah, you have to unmute yourself though.
Okay, let me share screen.
Yes, that's perfect. So I can hear you.
Okay, good.
And now I can see your screen. So I think you are all set. So without further ado, the next talk is by Sepide Mahabadi, who will tell us about, well, you can all see the title and you can all see the co-authors. So go ahead.
Okay, thanks, Piotr. So my talk is about non-adaptive adaptive sampling on turnstile streams. It's a joint work with Ilya Razanstein, David Woodruff, and Samson Zhu. Okay, so what is adaptive sampling? Adaptive sampling is an algorithmic paradigm for solving many data summarization tasks. So in short, what it does is that given a set of n vectors in a d-dimensional Euclidean space, it samples every vector with probability proportional to its norm or squared norm. And then it repeats it in an adaptive fashion, meaning that once it samples a vector, it then projects away all the remaining vector onto the subspace that is orthogonal to what it already sampled and continues on the residuals. Okay, so pictorially, if we have these 5 points, maybe in this first iteration, we sample the point with the highest norm, and then we project all the remaining points onto the subspace that is orthogonal to the first vector. And now we continue with the projected points. Again, we sample 1 point with probability proportional to its norm. And then again, we project all the remaining vectors onto the subspace that is also orthogonal to the second vector as well. And we continue this process for k rounds. Okay, so adaptive sampling is used for solving many data summarization problems. So we can put all these problems into a single framework as follows. We are given a matrix A that is n by d, and we can think of rows of A as the feature vectors of a set of objects in a large data set. We are also given a small parameter k, and the goal is to find a small representation of this data set, basically A, of size k, and we would like to optimize some predefined function. All the following problems, row subset selection, subspace approximation, projective clustering, and volume maximization fit into this category with different optimization functions. And adaptive sampling has been used to derive approximation algorithms for all these problems. So more formally, adaptive sampling samples in the first round, samples every row AI with probability AI, or norm of AI, a norm squared of AI over the Frobenius norm of A. And then in the subsequent iterations, it needs to project away from what it already sampled. And in order to do that, we can just contain the rows that we have sampled as a rows of a matrix M. And then projecting away from what we already sampled is just multiplying our matrix A or every row of A by this projection matrix I minus M plus M, where M plus is just a pseudo inverse of M. So now we would like to sample from the rows of matrix A times P, where P is our projection matrix with probability proportional to its norm. And we would like to do it in k rounds. So this process seems inherently sequential because we are sampling one row, we're projecting away from it, and then we're sampling again and again. So in this work, we would like to see whether we can implement adaptive sampling in a non-adaptive fashion. Basically, can we get a one-pass streaming algorithm for adaptive sampling? And so surprisingly, we show that yes, it's possible. It's possible to simulate adaptive sampling in one pass of turnstile stream. And we can show that we can have a process where outputs subsets of size k of rows of the matrix, such that the total variation distance between the probability distribution output by our algorithm and output by adaptive sampling is at most epsilon. Okay. And basically, we can do it in one pass of stream and space which depends polynomially on d, k, 1 over epsilon and log n. And besides the indices of these rows or this set of k rows, we can also report a noisy variant of the rows as well. So the indices and also noisy variants of the rows. So this is the main result, and it's also easy to see that it's impossible to return the exact rows in the turnstile stream. And then, a major component that we use in our algorithm is to basically generalize the L2 samplers for vectors to matrices with post-processing. So what is this problem? Basically, given a matrix A that is coming in a stream and a post-processing matrix P that is coming after the stream ends, the goal is to sample the rows of matrix AP with probability proportional to their norm. Okay, so in case you're wondering what this P is, P basically corresponds to this projection matrix that we are later using in our adaptive sampler. And then, so we show that we can do this sampling in one pass and space, which depends polynomially on D, 1 over epsilon and log n. So, and then finally, we show further applications of our results to get turnstile streaming algorithms that some of them did not exist before for all these data summarization tasks that we talked about. And finally, for the case of volume maximization, we show lower bound and upper bounds in the row arrival model. So this is the outline of the results in one slide. So let me conclude with a few open problems. So we don't know if the dependence of our samplers on the parameters are tight or not, like these two. And we want to see whether there are further applications of non-adaptive adaptive sampling. And finally, to give a more concrete question, we don't know if the results for volume maximization is tight. Basically, is it possible to get k to the k approximation for volume sampling in the row arrival model without any dependence on n? So currently we get a dependence which is n to the 1 over c, but we would like to see whether we can get, so we don't have a lower bound also that excludes this case. Okay, so that's my talk, and thanks for listening.
Cool. Thank you. We have a couple of minutes for questions. So we have a question by Seper Asadi. For your L2 sampling, does it work for all choices of P? Can P be a function of A itself also?
So it works, so it's, you mean, can it be used in an adaptive fashion, right? So L2, yeah, so L2, yeah, I think I can see. Yeah. So the L2 sampler uses count sketch, but just generalize it to for vectors as opposed to, so in each bucket, instead of keeping a one value, we are keeping a row. Oh, okay.
So the next question is by Amit. Does the main result work for sampling rows proportional to other norms besides L2?
So it's L1 and L2, yes.
Let's see, I have to do some bookkeeping here. Okay, good, good, good. Any other questions? There is one more question by Sandeep. If we allow a small number of passes, can we get better bounds?
So for the case of volume maximization, our lower bound holds for multiple paths as well. But for adaptive sampling, it's so because we wanted to, so for the L2 sampler, it was really important to get it in one pass, because then we are using multiple instances of L2 samplers to get adaptive sampling, and we wanted all of them to be in one pass so that later on we can simulate K rounds of adaptive sampling in one pass. So if you have multiple passes, then you cannot basically do it in single pass of adaptive sampling.
Cool, perfect. So thanks again for a very nice talk and good questions. And the last talk of the session is by Jacob. So I think Jacob is unmuted, but you still have to share your screen. Okay, I can see your screen now. Perfect. So the last talk of the session is on fast hashing with strong concentration bounds. Jacob will give a talk, and go ahead, Jacob.
Thank you. Yes, so I will present the paper of fast hashing with strong concentration bounds. And this is joint work with Anders Åhmann, Mathias Knudsen, Peter Rasmussen, and Mikkel Thore. So the goal of the paper is to find a simple and reliable pseudo-random hash function which has strong theoretical guarantees. By this we want a hash function which has like strong concentration results similar to the ones you would get if you had a truly random hash function. But it should still be efficient and it should be simple to implement it. So like the main theoretical challenge of the paper is like the analysis of the algorithm. It is to prove that a practical hash function actually has these theoretical guarantees even for worst case input. And this is like very important because if your input has enough entropy, then even like very simple hash function will work very well. But they will fail if you give it structured data. So the model we'll be working with is the balls and bins model. So you're given a set S of n balls, and for each ball X, we give it they have an associated weight Wx. The balls are then distributed into m bins using a hash function H. So we have n balls and m bins, and then they're distributed into the balls and then distributed into the bins, and then we're then interested in, for example, like what is the weight of the balls that landed into the first bin. We want a strong concentration result to this. So by strong concentration result, we mean that we want something which is like similar to a Chernoff bound here. So we allow ourselves to get like this extra error term here, which should be inverse polynomial in the size of the universe. But otherwise it should be like behave like what you would get from a truly random hash function. So what we prove is that we introduce a new hash function tabulation permutation, which has this strong concentration guarantee that we want, and which is very simple and is very efficient in practice. So we actually implemented together with a lot of other used hash functions. So the red hash functions here are like simple hash functions which does not have the theoretical guarantees that we want. And double tabulation and like fully random does have the theoretical guarantees that we want. And we can see that we only like at most a factor of 2 like slower than most of the simple hash function which does not have the theoretical guarantees, and like 25 to 30 times faster than the ones that does have the theoretical guarantees. So to introduce our new hash function, we first have to look at simple tabulation. So simple tabulation works by taking a character, like a key X, and then we divide it into C characters. Here you can like think of C as like a small constant. For example, for a 32-bit key, we would have look at it as 4 8-bit characters. We then have C fully random hash tables, and then for each of the characters, we look up in the appropriate table. And in the end, we then XOR all the values together, and this would then be our hash value. So this uses very like C times the size of the alphabet space and can be valued in O of C time. And like for 8-bit characters, like everything can fit in the fast cache. And this is why it works very well in practice. So tabulation permutation works similarly. So first we have, again, we divide the key into C characters. Now, instead of, we then modify our tables a bit. So instead of outputting something in the range of M, it now outputs C new characters. And then we also have C truly random permutations. And now to calculate our value, we then first, as in simple tabulation, XOR the values together. This gives us C new characters. And then for each of these characters, we then use a random permutation. And this will then be our output. To like full claim that this is very simple to implement, this here is then the C code to actually implement it. So this is just like essentially doing a simple tabulation 2 times. And this is also why it's so fast in practice. So the analysis of it is essentially we prove 3 different theorems. So the first one is that we give an improved analysis of simple tabulation and show that if the number of bin is large enough, then we have strong concentration. The second one we show is that if we have a hash function which when mapping to enough bins is strongly concentrated, then if we have this random permutation, we get to get something which is strongly concentrated into few bins. And then finally, if we have something that's strongly concentrated and then we concatenate the hash function, then it preserves the strong concentration. So I'll try to give an intuition for why this permutation actually works. So assume that we have a hash function which like strongly concentrates into many bins. So here we are. And then we want to map into few bins. So like the first thing you want to imagine is like just take the first half and map it into the first bin and the second half into the second bin. But then you might have that all the positive errors was in the first half and all the negative errors was in the second half. And this is actually what happens with simple tabulation. And this is why it does not work when you map into few bins. Next thing you might do is like just say, take the bins and then map them fully randomly into these 2 bins. But then you might have that too many of the bins mapped to this one. So even though we have like a lot of the negative errors here, but we have simply just too many bins mapping here, so we get too many balls mapping here. So what we do is we take this, all the bins here, then we permute them, and then we just take the first half into the first bin and the second half into the second bin. So what happens here is that we have all the positive and negative errors have now been distributed nicely. So we like they cancel each other out and we get something that is nicely concentrated. So yeah, we introduce a tabulation permutation that works really well. We theoretically prove that it works, has to be strong concentration on worst case input. And we experimentally show that it's very fast, like 25 times faster than any other known scheme with similar concentration bounds. Yeah, that was what I had to say.
Cool, thank you, Checo. Very nice talk. Any questions? Okay, Salil asks, do you get anything new in the asymptotic efficiency of the hash functions?
So essentially we assume that C is O of 1 and we then get like that we can evaluate things in O of 1 time, but this was already known like previously by assuming like that C was O of 1, that double tabulation, but in practice double tabulation is very, very slow because you have like a huge constant. So this is like a very simple and also implementable hash function that can be evaluated in O of 1 time, but no, it does not actually get any new asymptotic improvement.
Cool. Any other questions? Oh, Salil said thanks. Thanks, Salil. Any other questions? Okay, so if there are no more questions, then you know, like let's thank all the speakers and participants again. And this was the last talk of the session. So now we have a break, and then starting from 1 p.m. There are 2 workshops. Workshop 5, algorithms with predictions. And workshop 6, the randomizing space bounded computations, right? So these workshops will start after a break. They will start from 1 p.m. And at 4 p.m. And then I think at 5 p.m. We have the last session of this conference. All right, so thanks all, and enjoy the rest of the conference, and enjoy social distancing at home. Right, bye-bye.
You can feel free to hang around and ask questions, or like in general till like more 20 minutes if needed.
I see. So this is this anonymous voice comes from Arvind, who's our technical help. So let's see. So there is a question. I see. There is a thanks. I see. Okay. Yeah. So I guess right. So